All right, let's take a look at single replacements here. Single replacements of redox reactions. Redox reactions with electron transfer reactions. And don't worry about that balance. You know, balance is just, everything has to be balanced, not just redox. Everything. Iron nails drop into hydrochloric acid. And so iron nail is dropped into hydrochloric acid. Here, okay, do we have to worry about what were we worrying about? We were worrying about oxidizing. Do we have to worry about oxidizing acid in this case? No, because HCl is a mineral acid. Do we really have to worry about, what was the next thing we worry about? Water. Do we really have to, does iron, does it react with water? If you drop an iron nail in the water, is it going to start bubbling hydrogen gas? No. So we don't have to worry about water. And the last thing is iron a reducer or is iron an oxidizer? All metals are electron rich or electron poor? Metals. Metals, do they conduct electricity or they don't conduct electricity? If they conduct electricity, it must be electron. What's the most electron-rich species on the chart? The most electron-rich species you should have memorized. It is lithium. Lithium, is it a metal or non-metal? A metal. All the electron-rich species, all of them are metals. Metals are electron-rich. And so, you know, this is a reducer. This is not an oxidizer. If this were like fluorine or something like that, then I'd start to worry. So single replacement should work well here, I think. It should work well. Now, the thing we got to figure out is, this is A plus BX yields, yeah, and so what is AX? Well, we have a choice. We have iron 2 chloride or iron 3 chloride. Which one should we go with? Iron 2 or iron 3? Iron 2. Why? Because this is it. Iron goes to iron 2. Do you see iron 2 going to iron 3? I mean, iron going to iron 3? No. Iron 3 is very common, though. Where's iron 3? Iron 3 is up here. And so once we form iron 2, then that iron 2 itself can go to iron 3. And so the first step is just to go to iron 2. Well, that's all we're going to do. We're just going to do the first step. And so this is going to go to iron 2 chloride, FeCl2, and hydrogen gas. Now let's look at the driving force. Let's compare A to B. Which one's more active, iron or hydrogen? In other words, if you had a trunk full of iron nails or a trunk full of hydrogen gas, which one? You don't even need the chart for this, I think. Which one do you think is more reactive? Hydrogen gas. So we're going to from less to more. So we can see it here as well. Iron is, wait a minute, is it? Which one is more active? I had it wrong. It's iron is more active than hydrogen gas. So that doesn't make sense, but it could make sense because metals are actually, under the right conditions, are quite electron rich and flammable. And so if I had some iron filings, which you need to bring in, iron filings can also combust. And so I had it wrong. This is less. This is more. And so we're going from more to less active, which means we got driving force. If we got driving force, then we expect reaction to occur. If we expect reaction to occur, then I'm going to balance it. So how can I balance this? I'm going to have 2 HCl. All right, if I have single replacement, then I need to do this. I need to write the CE, the IE, and the NIE, just like we did for double replacement. And so this will be the CE. In the IE, we do the same thing that we did for double replacements. This is what we're going to do for single replacements instead. Is iron a strong acid? No. Strong base? Soluble salt? No, so just leave it alone. Is HCl a strong acid? Yes, so break it apart. 2H plus 2Cl minus. Is FeCl2 a strong acid? No. Strong base? No. Soluble salt? Yes. Break it up. Fe2 plus 2Cl minus. Hydrogen gas, strong acid? No. Strong base? No. Soluble salt? No, so leave it alone. And so in the NIE, we get rid of the spectator. What is the spectator here? Chloride's the spectator. And so this is going to be iron solid plus 2H plus. The chloride doesn't react. This gives us Fe2 plus H2 gas. And indeed, if I put iron in HCl, I'm going to start bubbling hydrogen gas off, and iron metal is going to dissolve. And so it worked here. Single replacement, no problem. Just as we expect. This is the producer, this is the oxidizer. Chloride's the spectator. So we have Fe plus 2HCl yields hydrogen and FeCl2. The only thing missing here is the driving force. We write out the ionic equation, and then we write out the net ion equation. Zinc and copper 2 nitrate. So this is a strip of zinc metal being placed into copper 2 nitrate. Let's take a look at that. Zinc metal is dipped into a solution of copper 2 nitrate. So I'm going to try that one out. Let's see. Zinc metal is Zn solid. Copper 2 nitrate is what? CuNO3 2. Okay, if I follow the A plus BH pattern, this should yield what? AX? Yeah, zinc is what charge? 2 plus. So it's going to be zinc nitrate and copper metal. And so let's compare zinc metal and copper metal on the activities theory. Actually, where did that activities theory go? So comparing zinc metal with copper metal. Zinc, yeah. So we're going from more active to less active. So that means there's a driving force present. We expect reaction. And so let's go ahead and balance it. Is it balanced already? Yeah. And so this is our complete or conventional equation. Let's go to the ionic equation. Zinc. Strong acid? No. Strong base? No. Soluble salt? No. Copper 2 nitrate? All nitrates are soluble. So this is soluble salt. This is going to be copper 2 plus 2 nitrates. Zinc? All nitrate salts are soluble. So zinc 2 plus 2 nitrates. And copper metal. On this one, do we have to worry about oxidizing acid? No. But wait a minute. What's a more powerful oxidizer? Because in single replacement, what's the oxidizer? Copper 2. Nitrate is the spectator. So you see nitrate doesn't react, it cancels out. And so that is copper 2 a better oxidizer than nitrate? verify that. Is copper 2 a better oxidizer than nitrate?
No.
No. But this is a tricky one because it's not just nitrate. We need some H plus. We need some acid. If there's no H plus present, is there any acid present here? No. If I added some HCl in here, then we're set. If I added some HCl in here, then no problem. We could have reaction. The nitrate can react. We need the H plus to form water. If there's no H plus, we don't form water. If we don't form water, then we aren't going to form something as stable. We're going to form something less stable, which means nitrate is going to be a lot weaker without H plus than with H plus. And so what we say here is this. It's missing the acid, the H plus. Missing H plus. And so in order to get the nitrate to react, I could do this. I could do zinc solid plus copper 2 nitrate plus acetic acid. Like this. I don't even need a strong. If I had some acid present there, then no problem. The nitrate can react. In fact, the acid can react as well because mineral acids will oxidize zinc. Zinc is a very good producer.
Isn't the copper nitrate aqueous? So is it technically there in water?
In acid and water, yeah, but it's in such minute quantities. It's not. It's not present in enough. This is like the recipe. Let's say we're trying to bake some cookies, and you need 1 cup of sugar and 4 cups of flour. Well, I don't have the 4 cups of flour. I'll just have the 1 cup of sugar. Is the 1 cup of sugar going to make good cookies, you think? No. And so the same thing here. We have 1 cup of sugar, but we're missing the 4 cups of flour. Now, wait a minute. I don't have 4 cups, but I have 1 teaspoon of flour. So I'm going to take one cup of sugar and 1 teaspoon of flour. Is that going to make a good combination, a good recipe? No. So we're making stuff here. When we're making this stuff, we got to have the right ingredients and the right proportions in order for it to come out the same. Now, what happened on the ship, the Grand Cam? Do you remember the Grand Cam? Texas City? The Grand Cam. Where's the H plus here? Well, ammonium is double duty here because ammonium is the reducing agent, and it's a acid. Ammonium is a weak acid, so there you got some H plus going. It's going to start off slow. Whereas if it was sodium nitrate is missing. There's no H plus there, so it's missing. So this is a difference in reactivity of the nitrate here. And so here we're missing the H plus, and so we would predict copper 2 to be the stronger of this. Now, when you get to more advanced classes, then you can figure out, well, because we're missing the H plus, its rank decreases. How much does it decrease by? And so here, because we're missing the H plus, how much does it decrease by? If it only decreases by this much, then it's still stronger. If it decreases by this much, it's weaker. And so in more advanced classes, you come up with some tools. These tools are called thermodynamics, which you can predict, how much it reduces the reactivity of this. Well, for us, we're just going to say, hey, we're missing the 4 cups of flour. We only have 1 cup of sugar. It's not going to work the same way. And so the same thing goes with this. It's like this. Remember copper and nitric acid. There's a reaction here. But copper with sodium nitrate, there's no reaction here. If I took copper with HCl, there's no reaction here. If I take copper with sodium nitrate and HCl, there's a reaction here. Because now I have all the ingredients. I have nitrate and I have H+. Nitrate and H+, I got that combination. Here I don't. I have the H+, but I don't have the nitrate. H+ alone is not enough. You know, H+ alone is not enough to oxidize copper. Here I have nitrate. Nitrate alone is not enough to oxidize copper. But a combination of nitrate and H+ is. Well, HNO3 is a combination of nitrate and H+. That's enough. Does this follow the A plus BX pattern? No. And so this means that not only do you have all the single replacement patterns you got to memorize additional patterns for a reaction like this. Eventually you got to memorize so many patterns it becomes worthless. How many patterns you have to memorize. And so we look for a more general method. Well, anyway, let's go back to this. The NIE for this one is going to be zinc solid is going to be oxidized by copper 2 ions, which will be the strongest oxidizer. Copper 2 is much stronger than water. Water is way down here, so we don't have to factor in water. And zinc is a much better reducer than water. And so water is not a factor here, and this is going to form Cn2+ plus copper solid. Precipitation is not a factor here. Just because copper metal precipitates doesn't drive the reaction. What drives the reaction is going from more to less, stronger to reducer, to weaker producer. So this is what they got. All right, so we have an alternative method. I'm going to show you to a single replacement. And the alternative method is actually a more general method. It's not a pattern. You don't memorize a pattern. It's just a sequence of steps that you run You could do all single replacement reactions using this method. And so it replaces the single replacement method, but opens up for many, many types of reactions. And so, but can be used for all redox. Still, we might, all redox, I shouldn't say all, because all redox that you'll find on the chart. It depends on how comprehensive your chart is, too, and then there are other factors that might screw things up. But this alternative method is just the chart method. The chart method is, we use the chart, the redox chart is the chart method. And so using the redox chart, it breaks it down into some steps. And so let's take this one. What is the reaction that occurs here? So if I took copper solid plus sodium nitrate plus HNO3, how can I predict the reaction here? So if I treated these as two separate single replacements, this would fail, you know, because A plus BX here and A plus BX there, it doesn't work. And so in this chart method, it's actually, there's no pattern, it's just a sequence of steps. The first step is inventory. So we got copper, sodium nitrate, break that up or leave it together. Soluble salt, sodium and nitrate. HNO3, strong acid, break that up, nitrate. And there's one more thing missing out of my inventory. What is it? Water. Okay, step 2. ID the OAs and RAs. And so here's where we consult the chart. Copper. Is that an OA, RA, both? And so we go to the chart here. Here's copper. Copper is on the right side, so it's a reducer. Is copper metal on the left side? I don't see copper metal. I see copper ion. Do we have copper ion or copper metal? We have copper metal, so it's a reducer. There's no copper ion in the reaction mixture. Sodium ion. Sodium ion's here. What is it? It's an oxidizer. Do I have sodium metal present? There's no sodium metal present. If there was, I don't know. It sends up a red flag. Sodium metal is extremely violent. That's where the reaction is going. So this is an oxidizer. Nitrate. Nitrate's an oxidizer, but I also need something to help that nitrate, which is nitrate and H+. And now it's a 1:4 ratio, but I can always change the ratios, you know, later. And so this is an oxidizer, nitrate and H+. Then I have H+ alone. H+ alone is also an oxidizer. H+ doesn't need any nitrate. And so H+ alone is an oxidizer as well. Why did I write nitrate twice? I don't need to write nitrate twice. And then I have water, which is an oxidizer and a reducer. And so this is my inventory here. All right, 3. React the strongest OA with strongest RA by adding what we call the half reactions. Half reactions. Balance electrons by multiplying coefficients. This is not well worded, sorry.
What's it say? 1/2?
Well, this is what I mean, so let's just do an example. Which one is the strongest reducing agent? How many do we have? We have 2. Copper or water? Copper. Copper is a metal. It's the strongest reducing agent. Which one's the strongest oxidizing agent? Nitrate with H+. That's it. And so what I mean by this is this. I just copied what happens to copper off the chart. The first thing is, well, it's backwards because copper is not a product, copper is a reactant. But what I can do is I can just flip this equation around. If I flip that equation around, then the half reaction says copper goes to copper 2 plus 2 electrons. And so I have copper solid, that's my reactant. So I copied off the chart. I just have to reverse it though, because I don't have copper 2, I have copper. But I do have nitrate and H+, and so I'm just going to copy that. And so I copy this off the chart. Nitrate needs 4 H+, And this is going to produce, plus how many electrons? Nitrate plus 4 H pluses plus 3 electrons is going to produce NO gas plus 2 H2O liquids. And so this is the strongest reducer. This is the strongest oxidizer. Reducers lose electrons. Oxidizers gain electrons. But there's a mismatch. Do you see the mismatch here? The reducer lost 2 electrons. The oxidizer gained 3 electrons. To correct this mismatch, we do this. We multiply the half. We call these half reactions. So the top one we multiply by 3. The bottom one we multiply by 2 to get the lowest common denominator, which would be 6. And so what we're going to get here is we're going to get, so let's add it together. We're going to get 3 coppers, and we're going to add everything on the reactant side, plus 2 nitrates, plus 8 H plus 6 electrons. This is going to yield 3 copper 2 plus, plus 6 electrons, plus 2 NO gas, plus 4 H2O liquids. And so I just went ahead and multiplied it through. And this is what you have to see. You have to see the electrons balance. 6 electrons were gained, 6 electrons were produced or lost. And so these must cancel. They must cancel. If they don't cancel, then something's wrong and you've got to start over. They must cancel. The reason is you can't go to the store and buy a bottle of electrons. If you could, then they don't have to cancel. But this is the likely reaction. We don't know if a reaction is going to occur. You're going to determine if a reaction is going to occur by looking at the driving force. And so we're on number 4, determine driving force. Is there a driving force present? Now the driving force is going from a stronger oxidizer to weaker oxidizer, and a stronger reducer to weaker reducer. And so the copper is the reducer. The nitrate and the H plus, this is our oxidizer. Now if we go backwards, what's the oxidizer, what's the reducer? If we go backwards, we look at the half reactions. If I reverse this, then copper 2 takes electrons. And so going backwards, this is the conjugate relationship here. Copper 2 is the oxidizer going reverse. And then NO and H2O lose electrons going backwards. So this is a reducer. It's the conjugate relationship. It's OA, RA, RA, OA. And so copper 2 is the oxidizer here. NO and H2O, this is our reducer here. Now we compare the 2 oxidizers. Which one's stronger, nitrate and H plus or copper 2? So I look, nitrate and H plus or copper 2, which one's stronger? Nitrate and H plus is up there, copper 2 is here. Which one's stronger? Nitrate and H plus. And so what we're doing is we're going from stronger oxidizer to weaker oxidizer. That's driving force. If this follows, we only have to look at one, but we'll check the other just to make sure. That means copper must be a stronger reducer than NO and H2O. So copper must be a stronger reducer than NO and H2O. Copper is closer to lithium, so copper is a stronger reducer. And so this is going from strong reducer to weaker reducer. And therefore we have reaction. And so the overall reaction is going to look like this. The overall reaction is going, let me just rewrite it, 3 copper solid plus 2 nitrate plus 8H plus yields 3 copper 2 plus plus 2 NO gas plus 4 H2O liquids. No, this is already an NIE. This method yields the NIE only. How late do we go today? 12:20? Oh, sorry. So I'll stop here.